So our next speaker is Jackie Michelle. So she's a geochemist and the president of Research Planning Incorporated. So Barrett mentioned RPI, and that's who Jackie works for. So Jackie, let me just make sure everybody can hear you in the room. So can you say something?
Okay, I'm going to talk about the 2000 Pepco oil spill in Patuxent River, Maryland.
Okay, perfect. Okay, I think everybody here, take it away, Jackie.
Okay, this is a great case study because it was a range of very intensive to sort of natural recovery approaches to shoreline cleanup, and then we were also very lucky we got some funding to go back and look at 7 years later. And so this was 126,000 gallons of a mix of number 6 oil from which was to a power plant. They were using number 2 fuel oil to clean out the pipeline, and it was released right inside the marsh interior. And we had some pretty strong winds that pushed into other wetlands, and therefore we had to deal with some very aggressive cleanup in some areas. And I must admit, this was not a Coast Guard cleanup. It was this one of these little lines where it was on just on the EPA side. So this was managed by the EPA. So here's the spill location. And I kind of want to show a picture of it. This is the pipeline here. You can kind of see it, the corridor. And you can say, well, I'll talk about 3 kind of areas. This is one area that was a lot of treatment done. This was some treatment. And these areas over here on the far left were little to no treatment. Okay, so, this is the opposite of the Deepwater Horizon. This oil did not weather, 1 second before it hit the wetland because the break occurred. You can see where all the repairs being done to the pipeline, went right into the marsh. Now, Barrett talked about in situ burning. Wouldn't this be a great in situ burn case? What do you think? Only problem, what are these long lines over here over the wetland? Can you see those? Yeah. Those are the power lines that provide power for all of the eastern Maryland. So we couldn't burn the wetland there because, a million people would be without power. So the EPA decided that they had to go in, because this is a area with a very low tidal range. And so there's not much tidal flushing, and so they had to create a lot of trenching, and you can sort of see how intensive this is. I mean, this is a very intensive treatment. I've very seldom seen something like this before. And the oil was very thick inside there. I mean, this was almost a centimeter thick inside the wetland, getting trapped in there. Amazing. And so with so little water flow, they had to use to kind of create their own high-volume, low-pressure flushing. So they dug these trenches to be able to push the oil down to areas for collection. Lots of trenches. And so you can see in the upper part of this photograph, you can see where all the trenches were. Well, they could get access to this other area a little bit to the east by putting out boardwalks. And so in these cases, there was no mechanical flushing. It was mostly all, sorbent recovery using hand tools. And so these guys are, sopping up the oil really thick on the surface. But there's another part of the area where there was, no access. So, they could get to this side, but not to here and not to another area. So look at this is the furthest to the east. You can see that the oil came into these little tidal channels and sort of into these big areas, And so what are these little dots here, you think?
Anyone?
Those are muskrat huts. And so look how the muskrats had eaten all the vegetation in the sinus sororities area, and so the oil just kind of covered on the surface. So there was, there's no access to this area. Can't get there by boat hardly, much less in a small boat, much less a crew. So no cleanup was done in those areas. And so we worked with the trustees and to do the natural resource damage assessment. And so here's some spots in the shoreline oiling for the sparkine alternate flora. The shoreline oiling we've talked about. It's pretty gets a little bit more flushing and wave energy, and that vegetation came back pretty quickly. We all know typha or cattails. They're hard to kill. They're almost harder to kill than frag. And so that came back pretty quickly. But what did not come back quickly was the interior areas that were heavily oiled with the sinus sororities. You can see some of these pictures. These pictures are from July 2000, September 2000, and then July 2001, 1 year later. So I'm showing this slide just to, some folks went out and did some, try to collect some samples to look at benthic communities, and there was a replicate of 3, and so you can see here that there's very little power. When you have an area that has so much variability, I almost rather have no data collected rather than have very poor power data. But it does show that right after the spill, the amphipods, which we know are most sensitive, were knocked down in all the habitats, but in the areas of the Spartina, after 1 year, it started to come back. So, but none of these data were significant. So here's, people love pictures 1,000 words. So one thing that they did that was really important was that since there was so much physical disruption to the wetland, as a part of the response in that area that was trenched, the RP planted it, which is very important. So you can look at these little 2 stacks up here on the left side of the photograph. There they are again. And so, it looks pretty good from this perspective. And so there was pretty good vegetative recovery where they planted. Here's another picture in July, 1 year later. Pretty good recovery. One more. Because essentially they backfilled the areas with clean sediment, so these plants were growing in clean sediment. But if you go out in the areas outside of where the area was replanted, you can see that, and even 1 year later, you can see blobs of liquid oil. Because remember, this oil did not weather any; it went straight into the marsh and into the soils. And so, so one thing that people talked about was that they want to use, let's do nutrient augmentation. Let's put some fertilizer in the marsh. But most marshes are not nutrient limited; they're oxygen limited. And so this is some work that was done as part of the response where they applied nutrients from a helicopter and over a period of several weeks, multiple applications. And this is the total pHs. And essentially the ones with the red triangle are the ones that were not treated with nutrients and the other ones are. And the whole pattern is the same. The total concentrations were pretty high. We're talking over between 1 and 2,000 parts per million pHs. So there's pretty heavy oiling in the wetlands there. But then so one thing, there was a natural attenuation. There is some flushing, from rainfall and tidal flushing. But look at this is the weathering index. These points are all on the same line. There's no weathering. Once that oil hit the marsh, and this is just in the top 5 centimeters, you still don't have any, after a year and a half, there was little to no change in the oil chemistry. And so we went back in 2007, 7 years later, we looked at the vegetation condition. We looked at above and below ground biomass. We did sediment chemistry and some sediment toxicity tests using amphipods. And so you can sort of see these two, all the little yellow dots are our stations. We didn't do the replanted area, but this is, so that a lot of these areas were had not undergone much treatment. And we want to have a lot of power, so we did analysis. We looked at what kind of number of replicates we had to have. So we had 12 replicates in order to be able to overcome a lot of the natural uncertainty and variability, and especially in the below-ground biomass. And we took the scores down from the order of 10 centimeters and then 10 to 20 centimeters. And essentially what we found was that the Spartina, there was really no difference between the oiled and unoiled area, but the Sinosauroides, the alternate flora was, but the Sinosauroides had about 20% reduction in below-ground biomass in the oiled areas 7 years later. And that's probably due to the relative amount of biomass in the rhizomes versus the above-ground vegetation, and also their roots a little bit deeper, and so they were in the oiled area a little bit more. And so I'm sure, is Ed still there? I know he's some pH histograms. And so in the lower right is the spilled oil. That's the fresh oil. And on the lower left is the sample 7 years later from 10 to 20 centimeters in some Sinosauroides habitat. And you can see the pattern is very similar. That it's weathered a little bit, but not very much. Whereas these ones on the top are areas where there's lots of mixed oils, and so that's not nearly. The surface soils had much less oil and weathering. More weathering than the deeper soils. And then if we look at there's a technique where you can sort of say, okay, well, let's just look at what's the relative loss of pHs in relative to the fresh oil. And because this is like the opposite of Deepwater Horizon that went 5,000 feet of water and then 100 miles shore, so this red line in the middle shows that the oil, had lost about 60% of the pHs, and those are mostly the volatile ones. But then over 7 years, none of that changed a bit. You can see the top line is the naphthalenes; those are the semi-volatile ones. But the green line are the three-ring pHs that are not lost by evaporation, and they're most of them are still there. even after 7 years. And then the toxicity for when you take samples to do toxicity, they take it and homogenize it and everything else. So it's very different than how oil occurs in a marsh soils, which has a lot of cavities, and oil penetrates those cavities preferentially. So these data are always a little bit hard for me to interpret because they're they're so mixed up. But essentially, with around 100 to 150 parts per million total pH is when we started showing toxicity to amphipods. And so, again, to wrap up the time series photographs, here's the site in April 2000. 1 year later, in the summer of 2001, you can sort of see the evidence of the trenching that was done. And you can see over on the left side, there's some still open areas. But by fall 2004, now 4 years later, you can already tell. Look, all the muskrats are back, right? See those little circles? Those are muskrat huts. So the vegetative, it looked pretty good, though there's a lot of subtle differences, when you do some more detailed plots. But overall, from this perspective, the habitat recovered amazingly well, considering the intensive treatment that was done in the area right near the break. So lessons learned. When you do aggressive methods, it's really important to start replanting as soon as possible. It's part of the response. We have really pushed for that. It's not emergency restoration. You dug up the marsh and you have to restore it as part of the response. Interior oiling has a lot slower recovery because of those lower natural removal processes, especially if you have a little tidal range like they have in the upper Chesapeake Bay. Weathering rates really decrease with depth. They essentially go to zero. Oil penetration is not uniform, and so I think the secondary permeability in the root cavities can cause effects to the plants because a lot of times the oil will penetrate those root cavities, and so it doesn't really reflect the concentrations of oil that the plant's exposed to, at that most important interface between the soil and the root. Nutrient augmentation is only needed when nutrients are limiting, and most of the time it's oxygen. And I really think plants are pretty tough. I mean, they can survive as long as you don't do too aggressive methods that without replanting. I was very impressed at the recovery. That's it.
Great, thank you, Jackie.